Welcome back to the deep dive. Today, we are going straight into the structural foundations of the industrial world.
We really are.
We're talking about aluminum framing systems, the light modular bones of everything, robotic cells, precision inspection equipment, even these massive clean room
And you
facilities.
might think framing is framing.
Exactly. But our source material today centers on a patented technology by a company called Controlled Dynamics Inc. It's called Angle Lock. And it suggests that, well, nearly every modular structure out there is built on a deeply flawed principle.
It's a fascinating premise because here you have an engineering company and their whole mission, engineering tomorrow's foundations today, is basically a critique of how things are currently done.
Right.
Control Dynamics wants to be the premier provider of these advanced modular systems, especially in places where precision and long-term rigidity are completely non-negotiable.
And their core claim is it's radical,
Right.
especially if you've ever built with this stuff. They claim their angle lock system, because of a unique mechanical lock, is 10 times stronger than traditional T-slot systems.
10 times.
10 times. I mean, that's not a small improvement. That's a fundamental disruption.
It really forces you to rethink what's even possible with an aluminum structure. And for you listening, if you're an engineer dealing with machine vibration or structural shift or just constantly budgeting for maintenance on loosening joints,
This is for you.
this deep dive is going to explain why those problems are just baked into the current tech and how this new approach just sidesteps them entirely.
Okay, let's start there then. What is the Achilles heel of these standard, ubiquitous T-slot aluminum frames? Why has relying on friction, which is how they all work, failed us so badly in these demanding environments?
Well, it really all comes down to the simple physics of friction. When you tighten a bolt in a T-slot, the clamping force creates friction between the connector and the extrusion.
And that friction is supposed to stop it from moving.
It's supposed to, yes. But friction, by its very nature, is a highly, let's say, unstable engineering principle when you're facing dynamic loads.
So it's fine for a bookshelf in your office, maybe.
Maybe,
Uh,
but not for a robot arm swinging back and forth millions of times.
Oh.
Not at all.
okay.
Our sources detail 4 major areas where this reliance on friction just leads to systemic failure. The first one, and you could argue it's the most costly, is vibration loosening.
Right.
Think about any industrial machine, a compressor, a robot, a CNC spindle. All that movement creates dynamic loads, high-frequency vibrations,
Mm-hmm.
and they just gradually overcome the friction. It's a slow, insidious process.
And the result isn't just that the frame gets a little wobbly, is it?
Oh no. The consequence is catastrophic for precision. That tiny amount of loosening means the structure shifts out of alignment. If you have a laser measurement system, your calibration is instantly gone. Useless. If you're doing automated assembly, you suddenly start making scrap. So you have to shut down the line, bring in an engineer to retighten everything. You're wasting valuable time and money. Friction guarantees recurring maintenance. It's built in.
So that's failure one. The second one seems to be about just brute strength, the limited load capacity.
Right. Friction has a ceiling. To resist higher loads, you've got 2 pretty bad options. You can use impractically high bolt torques.
And risk stripping the threads or damaging the aluminum itself.
Exactly. Or you have to grossly oversize all your components, which just defeats the whole purpose of using lightweight modular aluminum in the first place. You end up with something that looks like it's made of structural steel.
And, okay, if friction is all about surface contact, then anything that changes that surface, I'm thinking grease, dirt, even just wear, that must throw everything off.
It does. And that brings us to the third failure, unpredictable performance. Friction coefficients.
Yeah.
They're not constants. They fluctuate wildly with surface finish, contamination from oil or coolant, temperature, simple wear and tear.
So a joint you build on a Monday might act completely differently from one you build on Friday.
And it will definitely perform differently a year later. You just cannot guarantee long-term stability with friction. It's impossible.
And the final point in the source was about the geometry itself, the single failure plane.
This is really its weakest point. Friction clamps things together along one axis. But industrial machines, they face complex loads from all directions, sideways shifts, torsional twisting, shear forces.
Sure.
A friction connection is vulnerable to all of those at once because it's only really locked down in that single direction. The end result is always the same: downtime, expensive maintenance, and structures that just can't hold the rigidity you need for modern automation.
That paints a very clear picture of the problem. So we've established this massive vulnerability of friction. Now, this is where it gets really interesting. How does angle lock change the game? How do they actually replace unreliable friction with a purely mechanical lock?
The breakthrough is, well, it's elegant because it changes the whole point of engagement. A traditional system presses straight down, right, relying on that flat surface friction.
Yep.
Angle lock uses a special self-aligning bracket and this unique geometry that forces the fastener to enter the connection at a very precise calculated angle.
So instead of just clamping down, they're physically wedging into the material.
Exactly. It uses that angled entry to create a true mechanical interference, a physical lock. You're not trying to hold two smooth surfaces together anymore. You're using the actual geometry of the profile to interlock the joint.
And that's the core of this. 5 planes of mechanical anchoring concept.
That's it. That single-angled fastener creates locking forces simultaneously across 5 distinct planes. It locks the components together in 3-dimensional space.
Wow. Okay, that immediately deals with the single failure plane weakness we just talked about.
It completely eliminates it.
So now what about that? That fascinating, almost counterintuitive physics we saw in the sources. The idea that the connection tightens under load.
This is the key difference. It's about fighting physics versus using physics. In a friction joint, vibration works to reduce the clamping force, which allows slippage.
Right, it shakes it loose.
But in angle lock, because of that wedge geometry, when a dynamic load or vibration tries to pull the joint apart, it actually seats the wedge more firmly into the aluminum profile.
So it responds to vibration by getting tighter.
Precisely. It's a self-tightening, load-responsive mechanism. It doesn't rely on the bolt tension staying perfect. It relies on the physical dimensions of the joint itself.
Yeah.
This is what eliminates the need for retightening ever.
That is a true breakthrough, moving from connections that loosen under stress to ones that reinforce themselves.
It's a total shift in thinking.
And because this is all based on geometry, it gives another huge benefit the sources mention.
Yep.
Predictability. They said these structures are FEA compatible.
Yes, finite element analysis. It's crucial for any high-stakes engineering. You can't accurately model a structure in software if it relies on the random variability of friction.
It's a wild card.
Exactly. But because the angle lock interlocking is deterministic, it only depends on precise dimensions. And geometry engineers can model and predict exactly how that joint will behave under stress before they even build it. Yeah. That's essential for something like complex robotics.
We should probably touch on the materials, too, because this kind of performance needs some serious material science behind it. We're talking about an aluminum that has a 2x strength-to-weight ratio.
We are. The extrusions use a specialized architectural-grade aluminum. It's engineered to handle these intense mechanical forces without deforming, so you get structural performance that, as they claim, rivals steel.
Did 10x strength claim?
But you keep all the benefits of aluminum. It's lightweight, corrosion-resistant, and easy to work with. It's really the best of both worlds.
Okay, let's talk turkey. If this tech is so much better, why isn't every factory floor covered in it? Is there a big trade-off in cost or complexity?
That's a fair question. And yes, the upfront material cost might be slightly higher than generic T-slot, but the sources are very clear that the total cost of ownership is drastically lower. When you factor in all the benefits, the case becomes pretty compelling.
Tell us about those concrete benefits then, beyond that 10x strength number.
There are 3 huge operational gains. First, assembly time. Those specialized self-aligning brackets mean you can put structures together 50% faster than traditional methods.
50% faster.
50%. Aligning and fitting old friction connections can be really laborious. This just slots together.
So faster to build, stronger from day one, and then you get the lifetime benefits.
Exactly. Because the connections self-tighten under vibration, the structures deliver 0 maintenance over their entire lifetime. You just eliminate all that scheduled downtime, all the labor costs for retightening.
And what about flexibility?
It retains infinite flexibility. Unlike a weld, you can take it apart, move it, reconfigure it 100 times, and you don't compromise the mechanical integrity of the joints at all.
That seems essential for any modern facility where production lines are constantly changing.
Absolutely.
So if we connect this to the bigger picture, where is this kind of structural integrity not just a nice to have, but an absolute must?
Well, think about precision machine bases. If you're running a high-tolerance optical inspection, that base cannot shift a few microns over 5 years. Angle lock guarantees that.
Or robotics.
For robotics and cobalt mounting, definitely. The millions of cycles an arm performs demand a rigidity that friction just can't provide long-term. And this inherent vibration resistance means you can use these frames in extremely dynamic environments where a T-slot frame would literally shake itself apart.
The sources said this has been used in over 50 industries. Let's dig into 3 of those high-stakes examples to really see the impact. Let's start with the semiconductor industry.
Okay, semiconductors. It's a world of hyper-clean, hyper-precise environments. They need superior vibration damping to protect the wafer fab process. But more critically, every joint has to be contamination-free. When a friction joint loosens, it generates microscopic particles. In a clean room, that's catastrophic. It contaminates the wafers.
So zero maintenance also means zero particle generation from the fasteners?
Precisely. It's not just about rigidity for them. It's a contamination control strategy that standard friction systems just can't promise.
Okay, now let's shift to aerospace and defense. The stakes there are, human life and billion-dollar assets.
In aerospace, you're using these massive test fixtures to simulate flight conditions. If that fixture relies on friction, the inevitable joint drift means your incredibly expensive test data is instantly corrupted.
So you have to redo the whole test.
You have to start over. They need vibration-proof connections to eliminate that fixture drift entirely. And the 10x strength is crucial for holding huge, heavy payloads with the minimum possible frame weight.
And lastly, what about life sciences and clean rooms? What are the specific needs there that mechanical locking solves?
In that world, it's all about hygiene protocols and chemical compatibility. The systems use a clear anodized finish that's highly corrosion resistant, so it can stand up to aggressive cleaning. And in these controlled environments, you want to minimize human intervention as much as possible.
Because every time a technician has to go in to retighten a bolt, they're introducing a contamination risk.
Exactly. Zero maintenance supports strict hygiene by reducing how many people have to enter the controlled space. And if they do need to reconfigure something, the system's modularity allows for fast, almost toolless adjustments, minimizing that risk even further.
So Control Dynamics isn't just selling aluminum extrusions. They're offering full solutions, machine bases, clean room systems, safety guarding. They're selling guaranteed predictability.
That's the core takeaway. They're turning the determinism of that joint into a predictable, certifiable structure. It's not about the hardware. It's about selling the reliable foundation that modern automation needs to function at its peak.
So when we boil this all down, what's the core philosophy here? Why is this such a lasting engineering concept?
It comes down to a really fundamental realization. The simple, elegant advantage is that mechanical locks utilize physics, while friction is constantly fighting against it.
And friction always loses.
Friction always loses under dynamic load. The angle lock wedge, though, it capitalizes on that load. It reinforces the connection. And it's a deterministic answer to a huge, expensive industrial headache we've been putting up with for decades.
And that commitment to absolute stability seems to perfectly align with their company values.
Yeah.
Excellence, partnership, innovation, and especially precision.
Indeed. It's a paradigm shift, away from just managing structural problems and toward actually enabling maximum automation and operational life.
That leaves us with a concluding challenge for you, the listener, as you look at the complex machinery and infrastructure around you. Considering the absolute importance of deterministic, predictable performance in all automated and precision manufacturing, how many current industrial failures, systems running below peak calibration, and unexpected downtimes today are fundamentally traceable to the industry's continued reliance on single-plane friction? And how much global efficiency and capital could truly be unlocked by fully shifting the industry standard toward guaranteed multi-plane mechanical solutions like the angle lock system, something to mull over or explore further in your own work.